Welcome back to Cloud Computing and Big Data. Today we have our lecture 12 on Docker and container management. So this is an interesting topic because it gains considerable momentum in industry and in fact also more and more in the academic landscape to easy deployment of services, especially when you think about cloud computing, and then of course to related data sets, which might be growing to big data. We call this approach containers because it has lots of software, lots of data inside, and you will learn in this lecture basically how to manage all of this. That's why we also talk about container management relating to technologies like Kubernetes and other elements. But before we dive into the material of lecture 12, as usual, let us review what we had the last time. And our practical lecture 11.1 was directly related to your assignment 3, where it was, of course, based on Shadi's lecture that was introducing association rule mining, basically as one technique to take retail data sets like transaction data sets that you see here in shopping baskets, for instance, and turn them very easily with a couple of lines in the Python code by using the a priori algorithm and the MLX10 package, really in something that you can actually use. But of course, we also learned that the fine-tuning of that will take a bit more time that you don't have to do in the assignment. But if you potter off to the downtown area and say, I can give you a perfect recommendation engine, shop owner, you better be careful of saying this takes maybe a little bit more time than just using this Python script. Of course, still, the power that this script had was quite impressive. So we've seen basically with a couple of lines, I can really make a difference. I can understand shopping behavior that is not so obvious to me, mostly because, as we learned already in Shadi's lecture, most of these things are not just so straightforward as in the normal shopping list. We have this kind of 2-item sets or tripletons, as we call them, etc. So this means thinking around corners if you want to, and this means also the human brain cannot capture all these dependencies, or as we better should say, associations. So on the other end of the scale, you would say, nice, we have this a priori algorithm and it can do the job. And we had basically transformed the data a lot. We learned a little bit about CRISP-DM and transformed the data then basically in this one-hot encoding matrix, which is quite large, essentially. And with this, also we see that the whole algorithm approach, so to speak, is not really scaling. So here comes FP Growth to the rescue. Also, this is implemented in the MLX10 package that then obviously scales to big data. However, what you should learn also in this is, although you execute this in the HDF cloud, it has dedicated resources. This is also not a complete scalable solution, because then you need really a parallel FP Growth implementation, something that, for instance, Spark is endeavoring. So it is not at all so simple to scale up machine learning and data mining algorithms in the cloud by just throwing serial algorithms that we see here to the cloud. However, of course, the cloud has the potential of having a lot of physical resources that have lots of memory and lots of computing power. Still, if you're able to scale across nodes, usually you need another parallelization paradigm. In the second part, then last time, we talked about recommender engines. Sorry. And the recommender engines, we connected a little bit to watching movies. That's what everybody knows. And the idea was that basically we can have this matrix that obviously is something we would say seen or not seen, so very trivial here instead of ratings, but we can turn this into certain ground truths that we more or less then compare to. So in other words, we have a supervised learning problem, so to speak. We have the perfect matrix that we see on this page. And then on the other hand, where we say we want to have basically a matrix factorization here by learning embeddings that in a way with the dot product can come to something which is almost the perfect matrix that we see here. And this is a learning goal that you see essentially here, representing then values that actually add up to the rating or to the seen and unseen that we basically see on this page. And once you have done this, you can derive interesting aspects like really learning, so to speak, more about the videos or the movies and learning more about the persons. And then I can go to similarity ideas where I think I don't just recommend a movie that many others have seen and many others would say it's perfect. rather think about what have similar persons to me actually reviewed good or have seen. And that is what I recommend. So this as a recommendation engine brings us into the space of personalized recommendations, which is a huge space, and we just scratched the surface in the last lecture. And of course, here you will be basically referred to a more deeper data mining lecture. Obviously, in your assignment 3, the idea is to get more into the CRISP-DM process, to execute the association rule mining, the MLX10 package, together with a priori and FP growth algorithms, to do it a little bit on your own and then get a little bit of feeling for it, that there are, of course, still lots of hyperparameters that you can tune, right? In the association rule mining, we have something like lift, leverage, and things like that. And of course, in the recommender engine, you can play around a little bit with the dimensions of the embeddings that you would say here. You would say, basically, could you really put a person into 2 dimensions? Certainly not. Could you put a movie into 2 dimensions? Probably not. I think that's why in the Google Colab, really in the assignment 1, we had, for instance, I think 30 dimensions, right? So much more computation intensive with this, but also, of course, more representing than really the unique aspects really of persons or of movies. And this goes to the right direction, where again, there's lots of interesting material. If you take a real machine learning course, personalized recommendations is a very hot topic today. And let us look and go a little bit further to think about different perspectives that we have in cloud computing. So in the last lecture, we talked a bit about big data analytics, cloud data mining, related also to your assignment. That's why it's a bit more practical. And also this 12th lecture is a little bit with practical substance, because if you are going to the industry, chances are that you face Docker containers, that you face singularity containers, which recently have been renamed to Uptainer containers, at least partly. And the whole role of container management is something that you certainly need to know. However, a course like cloud computing cannot teach DevOps and container management and this as a whole. This requires 4 lectures. And I will just scratch the surface with Kubernetes today, but still it gives you an attention of one perspective of how you really scale up in clouds, how you ease the deployment of applications combined with data. And that's all where basically container management stands for. Hence, we have a challenge here, a big cloud data center with many applications. We learned a little bit about virtualization already, which helps of sharing resources. But here we go one step ahead and think about what I do with containers. What's the difference between just using virtualization versus containerized applications, which we will basically learn as part of the first lecture. But after the introduction of Docker, which is really, let's say, just one container example, but of course one that in a way is the de facto standard right now. I was alluding to that singularity is also there, but still Docker is by far the most used in industry practice. Now, when you have all these containers, you have a certain orchestration challenge as well. So you have to have a good idea of all the versions of the software in the systems. You want to combine different containers in the right version setup. You know that already from the deep learning challenge. If you remember, all the different packages have to have the right version of Python with the right version of PyTorch, etc., in order to be used really properly. And of course, in a cloud computing course here, we will look at some examples from AWS container services with an application example, which is quite interesting, called KubePad. And then we will basically compare just a little bit the other clouds in the first part. In the second part, then, we look at more selected advanced container concepts. As I said earlier, containers and container management, we could teach for 4 different university lectures. So here, pick just bits and pieces, which are, I think, very valuable to know because they are very unique in certain aspects. Firstly, because we also want to learn a little bit more about the Google Cloud, which comes a little bit short in the course here. We have done a lot with AWS and MS Azure. So let's have a look again with Google Cloud. But also let's look a bit broader and see what happens beyond the US hyperscalers when you think about Alibaba, for instance, in Asia. Then we talked a little bit about that here and there's a niche market for cloud computing, especially on these levels like platform and software as a service. And we will review one Uber cloud container approach, which basically has very specific solutions for computational fluid dynamics engineers that basically are around and need heavily cloud resources. And basically, this is already entering the field in high performance computing. So basically something which we teach more in the other course actually, but still has a lot to offer also in the cloud setup for engineers today. And just at the end, we will, of course, give some insights into Singularity and Mesos, but really just as a pointer so that you know that's not the whole world when you think about Docker, Kubernetes, and such. There's lots of different management software and orchestration software out there in the fields of containers. So let's look a little bit on the idea of firstly understanding this again. So when we think about services, we said this from the very beginning. We have a service and the people pay the services from their desktops and laptops, but most of it is running somewhere in a data center, which is hopefully very well connected by global data centers, something that you already know now because you have seen the Borealis data center from inside. So think about this as one node, and then you basically have another node and another node interconnecting all of these data centers. So from this, you would immediately say, okay, we had this picture and we contrasted it to the normal physical hardware versus virtualization. So why we need again to touch this? Why is virtualization suddenly not so good? And the answer is that it's not so good. That's not true. It's still a very good benefit, but containers show a couple of more benefits I wanted to allude to you. And this is something what you can basically see a little bit here in the contrast when you think about it. Virtual machines gave us really a really good runtime environment with the images, if you remember, with all the versions correct, like the AWS images we say, and then the application sandboxing somewhere in the cloud. However, we will also really understand in this lecture that actually virtual machines have some heavy load, and this is the guest operating systems, if you remember, for instance. And this means small size on this is really a benefit of containers I wanted to allude to, is actually pulling the software rather than having all the software already installed with Docker files and so on. We come to this step by step. So all of that contributes to a little bit low overhead compared to a complete virtual machine setup. Needless to say that the data centers still employ the virtualization scheme in order to resource share and so on, but they combine it smartly with the containers that we will see in this lecture. So let's put this into different pieces. Firstly, let's have a concrete example what such a container tool is all about and how it is different basically from virtualization. And then we look a little bit more how we can orchestrate these containers. So when you see here, Docker is really an open source container technology. It is basically deployed and available in almost all clouds today. You will see a little bit here the setup. And this is a very important setup for you to understand that we have an infrastructure, a host operating system, and a Docker on top that can handle lots of different applications. We call that containerized applications. So they're inside different containers, and the Docker runtime is actually using and basically managing all of this. So they are basically community image repositories where lots of applications can be already downloaded. Hadoop and Spark are just one examples of this. Here's an example of the Docker Hub, which is basically this kind of open source hub, or if you want a repository where you see you can download a Hadoop data node, a Hadoop slave node, a Hadoop name node. You remember Hadoop slave is a bit deprecated. People should call it rather Hadoop worker to be politically correct. And you see 5 million plus downloads. You see it's really used. So Docker Hub is really something which is actively used also by the community. That's why I'm showing it here. But no matter where you go in the Windows world, in the AWS world, you will see there different services around. And once you have done this solution, needless to say, you still have a huge cluster, right? You're basically just not happy usually with one container part. As we know, we need the data node, but also worker nodes or name nodes that basically capture all the metadata. So hence we need an orchestration of all these different containers where then the technology of Kubernetes coming in. So this is a very interesting material. Also, when you look into the Google Cloud, it is quite nice adopted, where you have sort of automated cluster management these days really with this container technology, much more simpler. And the idea, so to speak, is of course derived more or less from the initial idea of virtualization, but there is a certain analogy that you see here with a big ship, right? I mean, for you in Iceland here, that's nothing new. You see this in the harbor every single day, I guess. Maybe more with Eimskip containers than Maersk, but still the idea is the following, that you have the containers, they all fit nicely together. We have cranes that know exactly how to handle them. All what we do in software engineering and in cloud computing is to put a little bit more in the internal in this. So we want to have it transparent, right? So we want to see this container is doing it as a Hadoop data node. However, sort of as you will see a container, it's isolated. The data node is in itself, it's ready to deploy, just a couple of configuration parameters where it is running, like when I put the container off from the ship to the harbor. So they have basically everything you need to run. There's a source code, there's the data, there's a runtime, the right versions of the system tools, the right versions of the libraries. Everything is inside these containers that you basically find very well tuned for a specific version. And you can combine this now with other specific versions of containers. And this, in a way, abstracts it a bit. And this is now the core idea from the underlying idea of operating systems, of cloud components that you would have, right? The idea of container images, to keep them, so to speak, isolated or basically really abstract from the underlying layers, is now the idea that you have exactly on the ship. It doesn't matter if it's this Maersk Line ship or the Eimskip ship that you see in the harbor, still these containers can be nicely shipped from one ship to the other. And this is the idea that you see a little bit explained here. In the end, you have a physical server, that's what we know, that's what we always need. We have an operating system, obviously, and then there's a certain Docker engine, and no matter how these containers basically on top are configured, the Docker engine can handle them. And this is the idea of it. So basically being definitively independent from the underlying layers. And if there's a Docker engine running somewhere else, the idea is to really port easily these applications. And this really was one of the breakthroughs of Docker in commercial enterprises and commercial applications. If you think about that, sometimes SMEs, large industries, and many other players are often merging or basically also switching from one cloud offer to another, and their portability, especially based on these Docker images, can play a certain role. The other certain role, of course, it plays is to really enable an environment that's in this container really isolated, having everything ready to run, which makes it also easier to roll out, to deploy. If you remember the Hadoop data node, for instance, where we need maybe more of them, or also the worker node, we don't want to have just one, so we want to have 30 of them. So I just use 30 containers and instance, and or these Docker images will be then an instance of it. So hence, it also enables us to scale in a data set, in a data center, much more broadly. And this is also basically now the idea why the overhead, with this low overhead really, it enables also specific offerings of Uber Cloud and engineering, what we will see later, that really then drives with this paradigm the idea that with a very low footprint, I can do a lot of things with this CFD special application because I don't have to care anymore very much about the underlying layers. And this is one of the key benefits which enables now niche markets to be basically served by using this container technologies. So let's compare them a little bit to really understand that in full. Again, I think by now you should start of understanding the difference. So on the left side, we had this traditional virtualization where we said there's a physical infrastructure, what we always need, an host operating system, and then this hypervisor. Could be Zen, could be VMware, whatever. However, what we also learned that an image usually comes with some sort of a operating system. If you know and remember the AWS images, right? There was this AWS Linux or other versions of Linuxes and lots of TensorFlow, PyTorch, deep learning applications and libraries in order to perform deep learning. So in this sense, you have always this overhead of putting this guest OS quite prominent into these VMs. And in the VM images, which could be actually tens of gigabytes, just basically having a high storage footprint. And in a way, you would say, we are not really interested in that. We were interested in deep learning. Hence, we were very interested in the binaries, the libraries to fit the right versions with each other. So Nickel, NVIDIA drivers with the higher level PyTorch and other libraries in order to achieve a deep learning applications. We sort of were not really interested in the guest operating system, but the concept of virtualization carries this around. Hence, this gave the idea to the containers. So when we know basically that we can trust still the host operating system of doing the work, and we want to have resource sharing, what about just sharing the resources in terms of Docker images, basically, which are particularly focused on applications, on the right versions of binaries, libraries, but don't carry around anymore the guest operating system. And we have a sort of Docker engine, which is not really like an hypervisor, but on the same level. It would say we basically can understand what is described in this container. I know how to handle a container, and then basically can also run a container or get the right versions and libraries downloaded that are written in a Docker file. Hence, much more less storage, less storage footprint really as a whole, less overhead. And with this, the idea is also with these containers, of course, being not anymore vendor dependent. So in a way, without the operating system in general, but also other services, the idea is now really like the ship suggests. So whatever company you have, Imskip, Maersk, or whatever, or Smirl, for instance, you just put them on the ship. They have the same exact ratios. Everybody knows exactly how to handle them. And that is modus operandi day by day in business. Hence, something what all cloud vendors also have adopted. And this would be a very long lecture when I go through all the different elements. So I pick here different pieces in order to make the point that the container idea has really penetrated all the different cloud vendors. So you see that everywhere. I pick here the Google Cloud, for instance, on the PAAS level as software development kit, where you basically have a container registry where all your different Docker storages for container images are on the Google Cloud, where you basically can, register yourself new ones based on existing ones. It's a big, rich idea of how to use basically containers within your development cycle, and is basically also used quite broadly together with the app engine and so on. And of course, this directly relates not only to the development cycle, but also quickly to the deployment, right? And different versions of your software that you develop in the different versions of the app. And of course, also with a lower storage footprint, that means less cost for companies. Then another interesting example is in the AWS service, very similar. You already get the message that basically containers need some sort of a registry so that you basically understand what are all the container images. So think of it as a long list, a little bit like we have seen in the Docker Hub already, where you see lots of images and in different versions is described as metadata. What is this container about? Hence, we look also again inside the container. The container, in a way, is treated as a black box from the operational perspective and deployed with Docker files and so on. But still, we are interested very much what's inside the container. It's not just the customer, but some certain, piece of software. And you see here a little bit the different ways how you do now container services in Amazon. Where you have different images, run them, basically pull the images and run container everywhere. And you basically, of course, still need computation resources for it in the Amazon space. But of course, this is very much automated on a very much higher level than just EC2, right? So here we're talking now about the Elastic Container Services. And of course, as we discussed today, if you have running containers and a couple of those, we need some sort of orchestration mechanism, which you see here in the Amazon EKS, which is then basically the Kubernetes services that you would combine with all of these different services. Still based on the registry to know which of these images I really want to deploy, which of these basically are pulled then in production in the deployment. And this is just one of these services you can go on. Orchestration, as I said, also is important, just right as I had on the last slide. But here I also want to make the point that Of course, when you now hard code the amount of computing power you have underneath, this would be maybe with a container runtime, again, a very limiting factor. So what people have used in industry, and you see here Ubisoft or the GoPro, which are actually power users of AWS services in the field of containers in the entertainment industry, then you basically see that there are several services where you basically have a compute engine that more or less is built for container, and then you have not really any more resource provisioning that we had done before with the images. So do I need this or that CPU? How long I do want the CPU, and so on, and which location. So you basically have a little bit more a system without really managing the server underneath. And this, of course, makes it even simpler to deploy then, of course, the Amazon containers. But of course, you can get the message. Of course, there's also costs, right? So all of these different services here and there apply costs. Needless to say, just because you have a kind of no manual resource provisioning on the lower level doesn't really mean that you don't have resources underneath to be used, which is clear, because still in the end, you need some form of a computing entity. Hence, let's look on one application example, how that could work on a bigger scale, which is interesting. Here is an idea of cookpad that you maybe can analyze if you want a little bit in your apps, which is essentially having here all these different recipes with some pictures. In one respect, you could say it's a Facebook for cooking, very specialized for cooking. And you can imagine that we don't know how many people will download how many pictures. So it needs, so to speak, a kind of scalable infrastructure for massive photo uploading, downloading. We want to basically classify this a little bit. That's what basically Cookbook does, and has, let's say, as you see here, for example, at some point in time, 12 million photos and 140,000 users. So then this cookbook was very famous at one interesting TV show, and then suddenly lots of spikes came, where then the elasticity that we discussed before in Amazon was really key to the success. Otherwise, basically, this app would be directly being, dragged down. So here, another example how a small startup come to a bigger, basically, application over time, like in this cookbed adventure. And when you look into the deep details in this, how this is deployed, there's no secrets as well. So in a way, it's things you already know a little bit, and you can imagine that is needed. So one of things which is quite interesting here in this lecture is it's another set of deep learning library, MXNet, which is basically something like PyTorch and TensorFlow we discussed already. So this is another interesting machine learning library often used for deep learning today. And here you basically have lots of code builds before in order to basically then fill the registry with different, let's say, interesting deep learning applications. And of course, what's happening in the interesting containers then is that you have the whole deep learning modeling, the whole idea of working basically with these different data sets that people upload, right? So all the time photos. In order to analyze these photos, you see upload data here in the fifth step, that you basically have that you store and basically then have readily available, and we have a load balancer. That means basically the more people actually use the app, then, right? Which is then basically in this step 4, predicting essentially, and in step 5, uploading data and so on. This is, of course, something which is the other end, where all of these modeling has been already done. So the model itself from deep learning is already uploaded. All what is basically missing is now from these users to actually then in the instance upload their data, and then we do inference. We do basically the prediction out of this. In order to do this, all basically they're heavily used containers all over the way. Obviously with GPUs, you can imagine it's GPU enabled EC2 instances where you basically can then run deep learning also within a containerized way. So it is a smart combination of virtualization, right? So this is, of course, people also doing. So it's not just Docker to the rescue and then basically everything is done. You see here, we still have the idea of using traditional virtual machine systems, but we can actually do a better resource utilization and better deployment and portability by combining now the idea of typical virtualization with the guest OSs and Docker engines on top, by still doing basically much more easier porting of these containers with different one. And you see also some people just use a traditional virtual machine maybe. And this is the point today. We have shared loads in the data centers, so not everybody is ready for Docker, right? So that's why we still have virtualized environments also, which of course makes sense for people that really don't need Docker from some certain perspective. Still, the point is, and is that you already see a little bit in small scale here, the more containers you do, the ship suggests, right? There's probably a system or someone who is dealing with the orchestration of all of that, knowing a little bit which containers are where and what purpose maybe certain containers could have in terms of weight, because if you don't want to put all of the weights ones on the one side, the heavy ones, so there's some certain information probably about these containers, and I'm not expert in that, but you can imagine that these containers are not just put arbitrarily all the time on these ships. So hence we need an orchestration that deals with all of these different containers. And here comes Kubernetes into the game, which is an open source container orchestration tool that is basically used for really doing the job of scaling out any application that is in these containerized applications. You have the deployment automated. You can scale up, scale down, obviously. And then the whole management, lifetime management, is it still active, is also basically possible to do with Kubernetes, which actually was originally designed by Google. So let's look into this a little bit. But as I said also earlier, this would normally require a complete lecture to understand Kubernetes. You see it a little bit here on the right-hand side, how you can see it with this master worker paradigm. Again, you have these kubelets and the Kubernetes nodes, which then basically are using Docker. But basically, of course, the Docker is then the application, and basically keep track of what all the different Docker nodes then are doing. And this is where the kubelets are actually helping and basically rolling out and observing via this master server or master worker paradigm is the master server that is then having information about the automatic scaling of services, can initiate this. And also, of course, the monitoring aspects that should be not forgotten. Are all the Kubernetes nodes still running? As basically all the containerized application still healthy? These are all things which basically Kubernetes is key to success these days. So, of course, this also helps with the rollout of new services here. So you can imagine it helps with the idea of basically having hybrid deployment. So once you abstract it to the Kubernetes part, and you would say with Docker as well, chances are that you could do maybe MS Azure combined with AWS and Google Proc, so whatever, or the Google Cloud. So basically you abstract more and more from the underlying physical and services hardware if you trust yourself that everything runs in Docker. And this combined now with Kubernetes, which is one level higher, so to speak, because the master, so to speak, is then responsible for the whole cluster management, is then, of course, today really modus operandi usually in data centers. So very interesting topic. You see a little bit how that works here in the application. And I think the top left here speaks for itself when I say who is using it. And this is just a very small part of it. This is the Amazon idea of using this elastic Kubernetes services, where again, of course, the containers play a big role. But basically, in order to manage all of these different containers in certain different versions, you would use the EKS services in order to basically deploy them either on, let's say, hard-coded resources that you have with EC2, or as we said, the serverless variant with AWS Fargate, and then connect basically to this idea of using the Kubernetes service, rolling out the applications, and then the Kubernetes applications inherently would have, based on Docker, the nodes which are then responsible for really doing an elastic up and down management orchestration of all your containerized services. So this goes a little bit quick through, but again, as I said, we need usually much more time. It's just more to point you to really directions. And here's another one with the deep learning applications, because we have this often inside our course, where you see this basically here now on PyTorch, a specific version, where you can also then, of course, deploy the different versions of TorchServe or whatever PyTorch. It could be also the different versions of TensorFlow that you see here, in order to really scale up and scale down deep learning, what you want to do. And you can see you also can combine it in the AWS with different other cloud versions like CloudWatch or the, of course, elastic load balancing, depending on how many people really actually want to be using this. And with TorchServe, you basically see on the top that you basically have different trained models already registered that you use, for instance, for prediction, for inference, and so on, really in a pipeline from machine learning as we used to do, which is sort of the inference part or the production part, which comes after the typical model training that you have there. And you would argue this is something which you maybe can do without containers, but once you reach the kind of inference or the prediction stage, the pipelining, then of course containers have lots of good parts to offer. Let's summarize this a little bit with a movie before we close the first part of the lecture today.
Now that you have a good understanding of virtual machines, it's time to turn our attention to another one of the compute services, which is containers, which has grown a lot in recent years with the rise of Docker as a standard for a lot of the industry now. And what are containers? Well, essentially, it's a standardized packaging for software and dependencies. So think in a virtual machine, I typically have my operating system, I install my packages on, I install all my dependencies on, and I try to make sure that configuration works. With a container, I kind of pre-do all that work, make sure everything works together, and then when I want to run it, I just schedule it to run on a machine that's capable of running Docker containers. It's also a way to isolate apps from each other, and it works across both Linux and Windows servers, and allows separate apps to share the same OS kernel. Now, what's given the rise to this? And ultimately, it's application modernization, because there are a lot of issues with monolithic applications. If we install all our application code into a single server, minor code changes then require us to do full recompile testing. The application becomes a single point of failure. Let's say one of those boxes there, the different colors you see on screen, one of those pieces goes wrong, well, potentially it takes down the entire system, and the application is difficult and often expensive to scale. So the answer to this is to break it apart into what we call microservices, where each service is its own individual application, if you will, and can be scaled separately. There's this concept of 12-factor applications. You make the app independently scalable, stateless, and highly available by design. And it helps to compare and contrast these, because when you think about monolithic, well, it's very simple to deploy, inter-module refactoring, vertical scaling, technology monoculture, or some of the themes we see there. When you look at microservices, it's all about partial deployments. Again, deploying the piece of the entire application that I need as needed. Strong module boundaries, horizontal scaling is the big difference. So with containers, and this is something to look out for on some of the exams, is if I want to scale out horizontally, containers are very, very good for that, because I can just scale out that particular service that I need to, as opposed to with monolithic, again, if typically, somebody comes and wants to scale the application, you just add in more CPU, add in more memory to the virtual machine to scale it. And the other big thing with microservices, it allows for a diverse set of technology, from a stack point of view. Let's then look at some of the keys to microservices. First of all, we have functional decomposition. As you can see by now, all those services tightly coupled together that are error-prone become individual services. That's the first part of everything. Then we look at horizontal scale. Scale what we need to, not what we don't. This could mean that for virtual machines, if we've got an application that's a mixture of services, we scale the virtual machines horizontally in a scale set. We could scale the containers. We could use serverless functions. We can kind of choose what we want to use there. In addition, now we can choose to decouple the data much more efficiently. I can pick the best database for the service. So if Service 1 would make better use of Oracle, we can do that. Service 2, Azure SQL. Service 3, Redis. Maybe Service 4, we've got Azure SQL there, but it could be like MongoDB or Cosmos or something like that. So you can really start to see the benefits that containers provide, in addition to just the speed and efficiency. When you deploy in a container, they deploy very, very quickly when compared to a virtual machine. They're up and running very quickly, and again, they're not as error prone because everything's been tested, all the dependencies are coupled together, so when we deploy the container, we're good to go. So to drill this home, let's look at containers versus virtual machines. Well, again, on the left, if you remember from the virtual machines module, we have our hardware on the bottom, our hypervisor, and then we deploy the operating system and application in each virtual machine. With Docker containers on the right, we still have our server, so that's our hardware. And now that could be running, say, VMware or Hyper-V, or could be an Azure virtual machine before it gets to the operating system there. So again, the operating system here is like Windows or Linux. Then we run the Docker engine on top of that, but now we can just deploy our application. So you can see we're scaling and scheduling the applications. We don't have to keep scaling out that underlying operating system. That's not to say you don't have Docker nodes underneath that scale out to support the applications. That's obviously got to happen. We have to have enough CPU, memory, etc. to kind of make all the magic happen. But once you've kind of figured out how to manage that service, and things like Azure Kubernetes service make that very easy, now you can focus on the application itself and scaling that out.
Okay, that was a nice summary, especially because it's also shedding light a little bit on the microservices term that we also didn't really catch on very much, but which also is an integral part of it.